Hello, this is a quick video on concepts around energy and reaction energies. So, the basic components we see here. The energy axis is essentially Gibbs free energy. You can read about that more in the book. This is around page 172. Gibbs free energy has various components, including enthalpy, delta H, which is like probably the largest component of it. And a lot of enthalpy is bond energies. But we can, in fact, just abbreviate this axis as energy. And on the other axis, we have the reaction coordinate, which is kind of the time course of the reaction. But it's not just time going in one direction. It's that reactions are in equilibrium, so it's kind of both directions. The reactants are shown on one side, typically on the left, products on the right. There's a transition state that's higher in energy almost always. We call this the energy of activation, meaning that the reaction has to proceed with that much energy input, in this case, to get to the transition state, after which it's all downhill going to products. So, but there's different kinds of reactions depending on the molecules you're working with. On the right here, we see a reaction that goes readily, often without any energy input at all, and we call that an exothermic reaction. Sometimes, like in your book, they call it exergonic, trying to introduce new ways of saying things. But there's resistance to these new terms. So an SN2 reaction can often fall into this category because the two molecules, the reactants, combine. There's a little bit of an energy hill to climb to transition state where they're both one coming in, one leaving, if you recall, for the SN2. Then mostly a downhill. And overall, you see there's a net downhill energy flow in the reaction. So SN2 reactions can often go pretty easily. Endothermic reactions really need some energy input. They have a high energy of activation. Tough for them to get up off the couch and get going. So often that's heat involved or other kinds of energy input to get it to achieve the transition state, after which it is then downhill. So if you recall Sn1 reactions, they form a carbocation intermediate first. And I don't know if we've described this exact one, but stuff similar to this. We have the initial step that's dissociation. And it makes perfect sense that that's not just going to happen spontaneously. Often we need a little bit of heat or some other kind of energy input. In the second step, if we can really do this with a negative charge, really probably not, the nitrile group can come in and form that new bond. That's going to be from the intermediate on to the products. So our energy diagram for an Sn1 reaction is going to look something like this. Here's our starting material. It takes energy to climb this hill to get to this simple transition state. We can call this transition state 1. That's just really where the iodine's dissociating. And then we get from there downhill after the iodine dissociates to our carbocation intermediate. This is a true intermediate in the sense that it can be stopped at this point. You can actually, go ahead and put this in a bottle and put it on the shelf, and it might last some time. Often as a salt, for example. So transition states are hypothetical. Intermediates are real things. Then you have a tiny energy hill to climb from here where the nitrile group comes in and bonds. and then clearly from that point on, it's all downhill to your products. And I'm not really indicating knowledge of which of these materials in the start or at the finish are higher or lower energy. This is all kind of hypothetical in and of itself. So this is a typical reaction profile for SN1, showing the formation of an intermediate. The big hill to climb at the beginning is our endothermic climb. And then on the downhill end, it's exothermic. And then whether the reaction is endo or exothermic overall depends on the different levels of energy at the start and finish, I guess you could say. So you can break these down into component after component. A lot of things can affect the rates of reactions, meaning forcing it uphill or even downhill quicker or slower. Heat, light, solvents, solvent effects, catalysts, pressure. There's all kinds of things. People put reactions in microwave ovens, and so on. So the book talks some about that. This is really where the laboratory science comes in. And really, it's true that there's a disconnect between the laboratory science and the lecture. You can read all day about this kind of stuff, but once you get into the lab and experiment with them, it's a whole new set of skills and knowledge. So catalysts are particularly interesting, though, because they lower the energy of the transition state. And if you look at an energy diagram like this, if you could lower the energy of this transition state, for example, down to here through the use of a catalyst, you see what happens. You lower the activation energy. So catalysts tend to do that, and we might look at some of those kinds of effects later. So this is just a really brief overview to get comfortable and familiar with energy diagrams.